Good morning. Thank you for joining me for the very last lesson of Geometry A. I almost feel like this needs a drum roll. It's so exciting. The culmination of our entire trimester, our course, in today's lesson. So our lesson's going to be about finding area in the coordinate plane for some of these kind of quadrilaterals and also triangles, the different kind of figures that we've studied throughout the trimester. So it's kind of appropriate, all the things we've been studying, the different kind of figures. We're going to look at how to find their areas today. But unlike, when you've studied area in the past, we're going to be looking at finding area in the coordinate plane. And so that presents some challenges and also some different opportunities, different methods. So there are a variety of ways to find the area of a shape in the coordinate plane. And we're going to take a look at three methods. Method number one. So method one. One method is to use the distance formula to find the various dimensions of a shape, the base, the height, diagonals, etc. And once you have the dimensions, you can then plug the values into the respective area formulas, which our area formulas are right here. Let's see if I put a little box around it here. And so you'll notice that in all the formulas, you need certain lengths. It might be the lengths of the sides of a rectangle. It might be the height and a base and a parallelogram. It might be the diagonals in a rhombus or a kite. And so in order to find those, if we're in the coordinate plane, we have other options rather than if it was, say, not. We would either have to be told it, or it would have to be something that I guess they would be represented true to size, and we'd have to be able to measure it or something. Excuse me. So that's our first method. A second method is to use composite figures. Composite figures are made up of simple shapes such as triangles, rectangles, and parallelograms to find the area. Break the figure into simple shapes and find the areas of the simple shapes, and then add the areas of the simple shapes. So let's say you have kind of an irregular kind of shape, but you can see in it, I see I could split that into, say, a triangle and a rectangle. Then you could do that, find the area of the separate pieces, and add them together. And the third method would be to add simple shapes to the figure you are given to create a larger rectangle. So let's say you have kind of an irregular shape, or maybe it's not even a regular, maybe it's parallelogram. But say maybe you extend out some of the and kind of create almost like a box around it, a rectangle, which you do know how to find the area of, and then subtract any additional simple shapes that you added in to create that larger rectangle. So other than these formulas, which we can always kind of refer back to, that the rest of the lesson is essentially just trying out these different methods on some figures that are graphed in the coordinate plane. So let's just jump right in and try some problems. So looking at this first example here, so with A, I have a triangle, and from the chart, I can see that the area formula for a triangle is 1/2 the base and the height. And if you look at that formula, you can see that the base and the height of a triangle have to be perpendicular. So most of the time, that height isn't even a side of the triangle. It actually is a segment within the triangle. Now, although I could figure out this length here, which would be, I could consider the base, I'd have to use then this segment right here to be the height. And I don't really know on that segment AC where that other segment, that height segment, would actually intersect. So I'd be kind of guessing at that, and that wouldn't be accurate. So this is where I'm going to try that final method that we mentioned, and that's where we kind of create a rectangle around the figure. So see, I'm going to draw a rectangle that makes sure it includes all three of those coordinates. And you might think, well, how is that helping? Well, first of all, I know now that I have this rectangle. Oops, I have a rectangle that I'm going to find the area of. And then what I could do is then subtract off these triangles that are on the side. And that would leave me with that triangle in the center, which is the area I was trying to find. So that's what I'm going to do. I'm going to find the area of the rectangle, and the reason why this makes this very easy is because now it's along horizontal and vertical segments, the dimensions that I need, because that's base times height or length times width. And so I can find the area of that just by counting these dimensions, so I could find out like that length right here by counting and this length right here, and that would get me the big rectangle. Then we can subtract off those triangles. So let's see, that's this segment down here, its length is 1, and also you want to make sure these are scaled by ones, which they are, 2, 3, 4, 5, 6, 7, 8, 9. So I know that that is my base, and then I can count the height, which is 1, 2, 3, 4, and that is my height. That means the area of that rectangle is 9 times 4, or 36. Now I got to subtract these three triangles. So triangle number 1, I'm going to just kind of label them as, say, 1, 2, and 3. Okay, so triangle 1, when I look at its dimensions, I have to know its base and its height. But since this is a right triangle, the base and the height are actually the two legs. So that would be that part right here, which is 2. That's the base. And then right here, that's 4, which is the height. And the area formula for a triangle is 1/2 base times height. So all I have to do is take 1/2 the base, which is 2, and the height, which is 4. And that makes 1/2 times 8, which is 4. So I'm going to subtract 4 from that 36. Now, triangle number 2, over here, it has these dimensions. It's also a right triangle. And, oops, it's one dimension. Its base here is actually 1. So that's 1/2 times 1. And then the longer dimension is 1, 2, 3, 4, 5, 6, 7. 7. So that's 1/2 times 1 times 7, which is 3.5. Okay, almost done. So now I just have to do triangle 3. So triangle 3 has dimensions 9. This one was 9 down here because we already counted that, right? And then over here we have 3 left, because if this was 1 and the whole thing was 4, that's 3. So that's 1/2 times 9 times 3, 1/2 times 9 times 3, which is half of 27, that's 13.5. So these are all the things I'm going to subtract from 36, and that'll leave me with my area that I'm looking for, which is that little center triangle in there. So 36 minus those 3 leaves me with 15 square units. So, a lot goes into trying to find these areas if you have to use that method, but it really is, in this case, the only accurate way, because we couldn't figure out what that height would have been accurately. Now in this next example, we have a rectangle, and of course we can find the area of a rectangle by using the length and the width, or the base and the height. So we would need to know this length, and we would need to know this length right here. And we have some options here. One thing we could do is we could use the coordinates and the distance formula. But we could also use, to find that length, what the distance formula comes from, which is the Pythagorean theorem. And so how we could do that is we could kind of create a little right triangle out of each of these dimensions. So if I wanted to find this length right here, I could create a little right triangle like this, kind of like we did with slope, right? And we could just simply figure out, well, we'd have to rise and run, and that would give us the lengths of these little parts of the triangle. So let's see, I'd have to rise 1, 2, 3, 4. So this would be plus 4. And then 1, 2. So it's like, now we could use Pythagorean theorem to find that length, because that's the hypotenuse, right? So that would be 2 squared plus 4 squared equals c squared. So 2 squared is 4, and 4 squared is 16. So that's 20. So 20 equals c squared, and if we took the square root of both sides, that would be the square root of 20. So actually, let's just leave this as the square root of 20. So this side, and the same as the side across from it, is the square root of 20. And just to get the most accurate answer, we'll just leave it like that, because that's not a perfect square, so it's going to be some kind of decimal, like 4 point something. So we'll just leave it like that. Now we're going to go down here and find this dimension. Okay, do the same thing. We can make a little right triangle just by counting the rise and the run. So there's 1, 2, 3. It is a minus 3, but it doesn't really matter because we're using distance, so it's like they're all going to be positive anyway. 1, 2, 3, 4, 5, 6 for the run. So we've got a right triangle that's 3 squared. So again, since we're not really talking about rise and run specifically, we're not doing slope. We're just looking for the length of those triangles. We can use 3. So that's 3 squared plus 6 squared equals c squared. So 3 squared is 9, 6 squared is 36. That equals c squared. Add those together, that's 45. And c squared equals the square root of 45. So that means I have 2 dimensions. Neither one of them are really nice numbers. But, so now I could just find the area by using the base times height. And if the base now is the square root of 45, which is, or the length, and the height, or the width, is the square root of 20, and when I multiply the square root of 20 times the square root of 45, I actually get a really nice number. I get 30. So that's actually 30 square units, and that's the area of that rectangle. So even though the sides didn't turn out so nice, even though the square root of 45, which was the length, and the width, which was the square root of 20, were not nice, since they're part of a bigger calculation, I just didn't bother approximating them, because then they wouldn't have been exact answers. I would have had to round them. But when I ended up multiplying them together, I got a nice number. So that's a good rule of thumb, is just kind of wait on those approximations till the end, and you maybe won't even have to. Maybe they'll come out nice like this. So certainly seeing how a lot of the things we've learned this trimester are kind of coming together, and the Pythagorean theorems, these area formulas, yeah. So let's try another one. Example C. So this is the parallelogram, or what appears to be a parallelogram. And so we're going to try to find out the base and the height. So if we wanted to find out the area of this parallelogram, we could use the formula, which would mean I would need to know this length right here, and I would need to know the perpendicular segment to the other side, which would be right here. And that would be the height. So I'd have to know the base, and I'd have to know the height. And as of right now, that's like not really attainable. Again, I don't really have coordinates that would allow me to find that height. So this is going to be one of those that I'm going to see about maybe either trying that box in method, or maybe even trying to cut it into smaller figures. So sometimes you're just going to have to use some problem solving. And what I see here in this figure is I see a place where I could get 2 triangles that would share the same base. So right here, oops, let me get a better thing right there. So I could split that into these 2 triangles. But then as far as where I'm going to figure out the height, so those I could use those as the base for each triangle, the one on the top and the one on the bottom. But sometimes when you're finding the area of a triangle like this that's an obtuse triangle, the height actually is outside the triangle. So it would be, say, this little piece right here. So this would actually create this height actually outside of the figure, because otherwise we'd have to try to find that, oops, that's not right. We'd have to find the height from the vertex to someplace that's perpendicular on the other side, and that wouldn't actually be you know, the perpendicular to the other side if you drew from one of the coordinates. So anyway, when you have a obtuse triangle like that, the height is actually measured outside of the triangle. So unless you, say, found this as your base and then you kind of drew a perpendicular this way. So you could also use that. It doesn't matter. It still makes the area the same. So since this one is horizontal and vertical segments, it makes it easier. We can just count it. So then the base would just be that purple segment, and we could count that. That's 1, 2, 3, 4, 5. It's 5. And the height is 1, 2, 3. And so we could find the area of that triangle. Now going down to the triangle below, same thing. We can just extend out that side to find out the height. Height's always a perpendicular segment. So then that height is 3 again. So it's like we have 2 triangles. So we have each are 1/2 the base, which is 5 because they share the base, times the height. And there's 2 of them, right? So each one of them is 7.5. And so there's 2, 7.5 plus 7.5. And that means that whole area equals 15 square units. So some of these are going to require you to be kind of creative. You know, you're going to have to try to see something that, you know, is not there to begin with. Like you didn't see that line there, dividing that up into 2 triangles, but when you explore all the other methods, this is really the only way that we can get an accurate area. So, you know, it might not come to you for a minute. You know, I'm going to be honest. For me, I looked at it a couple of times. I kind of thought about a few different ways, and I thought, oh, well, right there, I could just split it into two triangles along that horizontal line. Now in D ends up being one of these, what we call a composite figure. So if you look at that figure, it's not like something that we have an area formula for. So we have only one choice here. We have to use a composite figure. And so what I could do is just go in here and split this figure up into these 3 pieces right here. So you see we have 2 triangles and we have a rectangle. And actually all of the dimensions that we need are on horizontal or vertical segments. So they're just countable. Right? So let's start off and we'll just find each area. So the area of the rectangle here, so 1, 2, 3, 4, the width is 4 and the length is 1, 2, 3, 4, 5, 6. So the area of this one right here is 24. I guess I didn't need this arrow. I was going to just draw the area in there. So that part's 24. Then I could come up here and look at the triangle up top. So this triangle up top has a base of this whole length from A to C. That's 1, 2, 3, 4, 5, 6, 7, 8. That's 8. And its height is right here, that segment, which is 2. So its area, because it's a triangle, is 1/2 the base times the height, which would make 8. So that's 8. So we have 8 and we have 24. And now we have one more triangle to work on. So that one, its base and its height are the 2, because it's a right triangle, are the 2 legs. So the base would be right here at 2, from G to C there. That's 2. And the height is 1, 2, 3, 4 on this segment. So its area is 1/2 times the base times the height, which would be 1/2 times 8, which is 4. So now we have our total area of 24 plus 8 plus 4, and that's a total area of 36 square units. Okay, so example E. They just seem to get more and more fun. So I took a few minutes and kind of explored some of the different methods, just kind of see if there was ways I could kind of divide this up. And really the only way that I could see that we could actually get reliable lengths here to use is by doing that boxing in method. So if I did the boxing in method, I could create this big rectangle. Oops, let's see if I redo that one. We could keep going up too high. This big rectangle here, and we could find the area of that, and then we could subtract off these 2 regions, 1, 2, and 3. Now the first little region we're going to have to subtract off is actually a, you could either split it up and actually probably smarter way to go, because trapezoid formula is not that fun, is to maybe split this up into a triangle and a little rectangle. So we could say 1A, and this would be like 1B. So that's probably the easiest way. So step one is find the big rectangle. So I'm going to use the base and the height of that. So let's see, along the base, if I count those segments, that's 1, 2, 3, 4, 5, 6, 7. And the height is 1, 2, 3, 4, 5. So that area is 35. 7 times 5 is 35. Actually, maybe I should write that. Work there. So 7 times 5 equals 35. And from it, we're going to subtract these 4 regions, excuse me. So first of all, I could start with 1A. And so that's a little triangle here that has that as its base and its height. So we know that area for a triangle is a half base times height. So that would be a half. So the base is just 1. See, it's that just one little segment. And then its height is 3. So that area is 1/2 times 1 times 3, which is 1.5. Now we're going to go down to this little rectangle. So the rectangle is a 2 by 1. So length times width is, so 2 times 1, that's 2. So we're going to subtract 2 now from 35. And then I'm going to go over here and we can find triangle 2. So there's the height, which is 2, and the base, which is 1, 2, 3, 4, 5, 6. So that's 1/2. We're going to subtract that one too. It's 1/2 the base, which is 6, and the height, which is 2. So that's going to be 6. And then finally, triangle 3 is 1 by 1, 2, 3, 4, 5, 6, 7. So it's a 1 height and a 7 base, or vice versa. So that final thing we're going to subtract off is 1/2 times the base times the height, which would be half of times 7 times 1, which is 3.5. So if we just take 35 and subtract those off, I end up with 22 square units. And let's try one more for good measure. So this figure, again, you kind of have some different options, but I think this one looks like one of the ones where I'll split it up into smaller regions, and I see like a square right here, and then I see the triangle on the side hanging off there, right there. So there's the triangle there, right? So we've got the square, not the square, it might be a square, but I'm pretty sure it's maybe a rectangle. I'll have to check the lengths of the sides. But you use the same formulas for the square and the rectangle, so it doesn't really matter. But so I'm going to find this one, and then the triangle, and then the figure down here is a trapezoid, so, which we can see it's got one pair of parallel sides. So we could do it like that, or if you're not comfortable using the trapezoid formula, you instead could use 2 smaller triangles. And I think that's kind of the way. The less formulas I have to use, the better. And so I'm going to use the area of these 4 figures, and I'm going to just add them together. So let's see. The rectangle, or I guess it is a square now that I look at it, because it's 4 by 4. So those are each 4 units long. And 4 times 4 is 16. So that's our first area. That's the now the triangle is down here below. So I already established that this 4 is the base, and then we also have the height right here, which would also be 4, right? So this triangle is 1/2 the base, which is 4, times the height, which is also 4, and that makes an area of 8. Now this triangle over here is a 2, it's got the base of 2 and a height of 4, so it's 1/2 times 2 times 4, and that's going to be 1/2 times 8, which is 4. So now we're plugging away. Now we've got one more triangle to find the area of. So the areas, so this time the base is going to be that length and the height is going to be that length. Okay, so the base is 1, 2, 3, 4, so that's 1/2 times 4. And then the height is 1, 2, 3 units. So 1/2 times 4 times 3 is 6. And now we just have to add up all of those areas to get the area of that whole figure. So 16 plus 8 plus 4 plus 6, that adds up to the whole area. And that's 34 square units. So we'll go ahead and leave this last problem as maybe a possible you try in class. And if you actually, maybe I could just give you what the final answer is, and then if you want to try it, you're welcome to try it any way that you'd like to, and then you can confirm if you're correct or not. So real quick, I'll give you the answer to this. Okay, so the answer to this one is 32 square units. And if you want to give this one a try on your own, I did the boxing in method. I tried lots of other ways, but I did this method where I created a rectangle around it. Oops, maybe that's not quite exactly containing those coordinates. Remember, it's got to contain all the coordinates, which that does. And so if you just find the area of the rectangle and then subtract off your 4 triangles, excuse me, you should be able to get 32. So yeah, give that one a try just to test your level of understanding and your use of those formulas. And always refer back to that chart to make sure you're using the right formula. But a lot of these you can kind of accomplish just using the parallelogram formula, which is base times height, the rectangular square, which is also base times height, and then the triangle 1/2 base times height. So that does it for the last lesson of Geometry A. So thanks for being with me through this whole course. I'll see you in class.